I just wanted to ask for the proctored exams. Is that covering all of chapters 1 through 4, or is it 1 through 3? Or
Yeah, so all of my tests are potentially comprehensive. So what I often do, like if I see on your first face-to-face test that some students didn't get some stuff from chapter 3, then usually on my second face-to-face test, even though that covers, much later chapters, I would actually include chapter 3 problems in the next one. So yeah, they're always comprehensive like that, but I usually stay mostly away from the old chapter questions, unless, like I said, unless I saw a large group of my students were weak on one particular thing. So, what I would recommend is when you've been studying, for instance, online test one and online test two, any questions that you repeatedly had problems with, I would make sure you know those inside and out because I'll look at those to determine what I want to put on test three. And then on test three, which is the face to face test, I'll look at that and any questions that a lot of people missed, I'll put that on the next face-to-face test as well as the next online test. So, a good rule of thumb is always back at your test whenever you're finished with it and make sure you learn how to solve any problems that you got wrong. So, I recommend doing that on all your courses, at least in math and physics and engineering, chemistry too, that sort of thing.
What is this? I'm keeping this actually. I need this to go back to that. You're such a good cat. Sick master. So
Zach, I hear you, but I can't tell if you're
yeah.
talking to me or someone else. Sounds like you might be
Yeah,
talking to
well,
someone else.
Leon ran your 1,000 PR on a workout yesterday. Nice. Can I see that real quick? No.
All right, I muted him. He was clearly not talking to me. Hmm. We still got about 2 more minutes if anybody has any other questions. Okay. 1 minute left, folks. 1 minute.
Switch. So I can get less. I need less. I realized I stay on the ground for way too long, which is attributed to my flat feet.
Yo, Zach, you
So I
keep
had to
talking, man, and everybody hears you.
just
I muted you again. Hmm. All right. It's essentially time to get started. So I'll ask one more time. Does anybody have any questions before we get further started? Seems like not. Okay, so when we last met, I'd started on some Newton's second law problems. I'd already covered, at least in principle, I'd talked to you about what Newton's first law is for every, excuse me. Newton's first law is an object in motion tends to stay at that state of motion unless acted upon by a net external force, or you could say it, an object will maintain a constant velocity unless acted upon by a net external force. Okay. That's Newton's first law. Newton's second law is the acceleration of a body is directly proportional to the net force acting on it and inversely proportional to the mass, and that the acceleration will be in a direction parallel to the net external force. So that's the second law. And then the third law is for every action, there's equal but opposite reaction. And really, what that means is whatever a force you apply to something else, that same thing is going to apply the exact same force to you, but in the opposite direction. So, for instance, when you step off of a curve and you start to fall as a result of gravity at 9.8 meters per second, that's because of your weight. And your weight, which is mass times gravitational acceleration, is being applied to you by the Earth, and that means the action reaction pair of that force is the force of you pulling up on the Earth with exactly the same magnitude. But obviously, the Earth is so big that that itty bitty, and in my case, 110 kilograms times 9.8 meters per second is not very big of a force on the Earth. So that's the three laws. Remember, the third law is always about one thing acting on another, and then the other one is the second thing acting on the first. So they're never acting on the same thing. We did do a couple of Newton's second law problems. We worked with a box to learn about normal force, and now I'm getting ready to do an extension to that. Specifically, I'm going to work example 4.7. As I told you, I'm going to try to stick to the book examples. There is one example I'm going to work in a little bit that will not be from the book. There's a one like it in the book, but I'm doing it a different way, so it'll be a little different. But in this first case, we're doing example 4.7, so it would be useful for you to have your textbook open, or specifically your online textbook turned to chapter 4, so you can read the examples. I will read them out loud, but you might want to look further or something like that. So let me go ahead and share my screen. Still nobody had any questions, so I'm pressing on. There we go. We got that. So I'm doing example 4.7 here. Just as soon as my screen comes up, which is taking a long time. Okay, there you go. So this is example. I'll try writing with a pen instead of a laser pointer. This is example 4-7, and it says accelerating the box. So what happens when a person pulls upward on the box in example 4.6 with a force equal to or greater than the box's weight? For example, let FP, meaning the force that the person is applying, equals 100 newtons rather than the 40 newtons shown in figure 415C. So the diagram we're looking at here, or the figure we're looking at here, is this is a 10.0 kilogram block, and of course it's sitting on a tabletop. Now I'm going to draw a free body diagram for this. So I will draw a simple XY coordinate system like this. The X isn't going to be relevant here because all the forces are really in the Y direction. And the box will be represented by a dot. That dot has a mass of 10.0 kilograms, and that's indicated on the diagram as well. I'll use red to represent vectors pointing in the positive direction, coordinate direction, and I'll use green, or excuse me, in the negative coordinate direction. I'll use green to point in the positive coordinate direction. So first thing we do with our free body diagrams is we take the object that we're actually applying F equals ma to, which in this case is a 10 kilogram block, and we say what is actually touching that 10 kilogram block. So in general, you're just going to say what's touching the thing that we're doing F equals ma on. In this case, it's a block or a box, and someone is pulling up on it with some kind of rope, and that force is Fp. It's upward, which is a positive y direction. So I put right here Fp, and notice I didn't put the vector symbol over it, so that means I'm representing a magnitude of a vector, and they're saying the magnitude of that vector is 100.0 newtons. Now, that's all the objects touching it. In this case, in fact, the box is actually hanging, so it's not even correct for me to draw it on a surface like I had done before, so now I'm removing that surface. Sorry about that. I was remembering the previous example, which is what it was referring to. So that's what's going on here. Now, that's the only object touching it is the FP, the string that the person's pulling up on. Okay, now air is touching it, but air resistance isn't really relevant. Especially since air resistance turns out to be related to velocity, or maybe proportional to velocity squared, and this thing's not necessarily moving with any great rapidity, so it's not going to have much of a air resistance force on it. So we've basically excluded all the things that could possibly be touching it. Now all we have left is the forces that act at a distance. Those forces are things you're familiar with but don't necessarily know that much about. For instance, you've seen a magnet can actually cause another metal object to move without touching it. That's action at a distance. You've probably seen electric forces before, and they act at a distance without touching anything. And gravity, of course, is the other one. And that's what's acting here. The Earth is not physically touching this box, but it is pulling down on it. So that's action at a distance. That's the only one we got to deal with. So I'm going to draw that force now, and it points downward, which is a negative coordinate direction. And we've derived earlier that the formula for weight is m times g, which in this case is going to be 10 times 9.8, which is 98.0 newtons. So when they ask what happens when a person pulls upward on the box with a force equal to or greater than the box's weight, what we're asking here is what's going to happen. So I'm going to go ahead and write Newton's second law of motion as follows. So Newton's second law of motion says the summation of forces is equal to mass times acceleration. This happens to be a case where the acceleration is a constant, so I don't have to write in A as dv/dt. And not only that, it's only one-dimensional motion, so I can just reduce it to the summation forces in the y direction is equal to mass times acceleration in the y direction. And magnitudes of vectors are always positive. However, components of vectors have positive and negative signs, so they're not necessarily positive. I also want to reiterate that the left-hand side of Newton's second law, which says the summation of forces, that is a sum. It's only adding. But I often will represent that addition as a subtraction because when you add a negative number, that's the same thing as subtracting a positive number. So just keep that in mind. Now that I have the free body diagram, this is really easy. I can say 100.0 newtons plus, now this time I'm actually writing it out with the plus so you'll know what I'm talking about, minus 98.0 newtons is equal to 10.0 kilograms times A. That's the only acceleration we're dealing with, so there's no need to subscript it Y. Now, what we have here is 100 newtons minus 98 newtons. Again, I wrote it as plus this time, but I'm going to, in the future, write more or less just positive things and then minus negative things instead of writing a plus sign every time. So I just want to remind you guys. When we subtract these two, we get 2.0 newtons is equal to 10.0 kilograms times A. So A, I'm going to pull on the left-hand side now, is equal to 0.20 meters per second per second. Now, how that worked out was we basically had a Newton over a kilogram, but a Newton is a kilogram times a meter per second, and a kilogram, of course, is in the bottom. You can see that this kilogram will cancel out with that kilogram, and we'll just have left meters per second every second. So that's how that worked out. Now, what we're supposed to decide from this is basically if the force is exactly equal to the weight, in this case 98.0 newtons, then the object will just stay right where it is. Or if the object was actually moving at some constant velocity, it can continue moving at that constant velocity. However, if it was a slightly greater force than the 98.0 newtons, then that's going to cause it to speed up if the velocity wasn't zero. But if the velocity was zero, it's still going to cause it to increase the velocity in the same direction as the force. And increasing of velocity is one version of acceleration. You can accelerate by speeding up. You can accelerate by slowing down. You can accelerate by turning left or turning right or turning up or turning down. So those are really the ways you accelerate. Anybody have any questions on this example? Okay. Now, the next problem I want to work is actually example 4.8, and I'm going to do it right here. So this is going to be example 4.8. Now I'll read it to you really quickly. I'm going to go ahead and draw a figure right quick so you'll have some idea of what we're going to be talking about. This is supposed to be an elevator. Here's a scale that a person in the elevator is standing on, and here's the person standing on the elevator. The person has a mass M equal to 65 kilograms. I'm going to call it 65.0. And I'm going to tell you that at least in the first part, the elevator is actually accelerating downward. So A is equal to 0.20 times G. That means not 0.20 grams, but 0.20 times 9.8 meters per second every second. So that's the problem. Now, I'm going to go ahead and read it to you. It says a 65 kilogram woman descends in an elevator that briefly accelerates at 0.20 g downward. And let's go ahead and call that 0.200 since I already went ahead and made the mass 65.0 kilograms. I'm going to go ahead and make the multiplier of g 0.200. So a 65 kilogram woman descends in an elevator that briefly accelerates at 0.200 g downward. She stands on a scale that reads in kilograms. During this acceleration, what is her weight and what does the scale read? And B, what does the scale read when the elevator descends at constant speed of 2.00 meters per second? So A is that we want to know what is her weight, which I'd call apparent weight, and the force on, or let's say the scale reading. So let's say M scale is equal to question mark when accelerating downward. So that's part A. Part B, they're asking what will the scale read? What does the scale read when the elevator descends at a constant speed of 2.0 meters per second? So mass as read by the scale equals question mark when V equals a constant 2.00 meters per second downward.
Quick question, wouldn't that acceleration be negative?
It can be. That's generally the way we treat it. Is we treat the up direction as positive and the right direction as positive. So if the acceleration's in the downward direction, you would generally call it downward. In this case, I haven't really decided yet what my free body diagram is going to be and which direction my y-axis will be in. But in this case, yes, I'm going to make it negative. But yeah, generally
Okay,
speaking, most people use it negative all the time. A lot of people do, but occasionally it's better to leave it positive. All
thank
right.
you.
You're welcome. I'm going to go ahead now and make this into a free body diagram so we can better analyze exactly what's going on. And I am choosing up as the y-axis, as the positive y-axis. And therefore, like she said, we will have the acceleration being a negative quantity. Unlike what you might do in your statics courses, in physics, we generally do not put accelerations on a free body diagram. We only put forces on a free body diagram. We don't draw a separate diagram for accelerations either, but I sometimes will write off to the right which direction acceleration is going to be, or up above it, or down below it, or over to the left. So what I'm going to show you right here is the woman is going to be represented by a green dot, not a black dot. Okay, that's her. Her mass is 65.0 kilograms. Now, again, what I see touching her is just the scale platform. So that's touching her. Of course, the air is touching her, but again, we're going to ignore air resistance. So I'm going to say that there's an upward force that I call Fs, which is the scale, and that also happens to be what we would call her weight. Okay, So whatever that force is that the scale puts upward on it, that's going to read as on this scale a certain number of kilograms. But if you took that number of kilograms and multiplied by 9.8, that would give you an actual force, and that's what we're looking at here. Now we've eliminated or made use of all the things that are touching it. Now we have to talk about action at a distance, and the action at a distance in this case is again gravity. So gravity, which is weight, equals mg, and you can see already why it's not good to call that m, or not good to call that weight. So I'll leave that off. Okay, the weight at 65 kilograms is 65 times 9.8, and that's 637.0 newtons. Now I added one extra sig fig anyways, just to show basically, how I handle non-sig figs. I underlined it. So now that we have the free body diagram drawn, I'm also going to indicate that there is an acceleration, and the acceleration over here is A is equal to, if you multiply 9.8 times zero point 0.2, you should get 1.96. Let me double check with that. Yes, 1.96. So the acceleration is downward. I'll put a negative on it this time since we've now drawn the coordinate system, and that's negative like that. So there's our acceleration. Darn it. 1.96 meters per second per second. So our free body diagram allows us to actually write out Newton's second law. The summation of forces in the y direction is equal to mass times acceleration in the y direction. What we have is a force that the scale will sort of read, but it's calibrated to read kilograms, so it's not necessarily the newtons that we want, but the Fs is gonna come out in newtons. So we have Fs, which is pointing in the positive direction, and then we add to that the weight, but that's pointing in the negative direction. So instead of writing plus a negative, I'm just going to write minus 637.0 newtons is equal to 65.0 kilograms times the acceleration, which is negative 1.96 meters per second every second. So that's Newton's second law. We can go ahead and solve that for Fs, and what we'll see is that Fx is equal to 637.0 newtons minus, now I'm going to take the 65.0 and multiply it by 1.96, and that's going to give me minus 127.4, and that 4 is an extra digit as well. So we can take that and add it to 637, and when we do so, we get 509.6 newtons. So that is her weight. And actually, we would call that the apparent weight. Okay, and hopefully y'all have done this before. I was telling my lecture class today, I still do it to this day, even though my daughters are now fully grown. But basically, every time I get on an elevator, I tend to, when it first takes off in the upward direction, I'll sort of weaken and unstraighten my knees a little bit so I can feel how when it accelerates upward, I feel a little extra heavy. And therefore, it causes my whole body to squish down a little bit. This case it's actually accelerating downward. Now, you might think that means it's accelerating downward because the elevator is going downward, and that is a way of doing it. But it could also elevate or accelerate downward when the elevator's on the way up and then it starts to slow down at the top. So in that case, when I'm on an actual elevator, what I normally do is I can feel when it starts to slow down, and I'll jump up real fast, and I can, I'm not built for jumping really high. I'm built more like a cue ball or something like that. So when I do that, it's really remarkable because my head can touch the ceiling of the elevator. So that's why I always do it, just to teach my girls the physics principle behind it. So what we're seeing here, working this problem, is when it accelerated downward, I felt, or this lady will feel, less weight. And that is exactly what I was talking about, because I can jump so high because I'm less weight. The gravity's not acting on me as strongly when the vehicle or the elevator is slowing down. That's why I can jump even higher. And if you were to change the acceleration to be in the positive direction, you'd see that this sign right here, this negative and on the 1.96, in that case this would become positive, and you'd get, instead of the 65 kilogram woman only weighing 510, she would in that case weigh more like 780 newtons. So that's why my legs and stuff crush downward when the elevator takes off in the upward direction. Anybody have any questions on that one? Now, the apparent weight, we can assume the apparent weight is equal to the apparent mass times g. So if we want to know what our mass on the scale is, and I hate this thing keeps changing back that. So if I want to really know what my apparent, darn it, it did it again. If I want to know what my apparent weight is, then what I got to do is take my apparent, or excuse my apparent mass. I take my apparent weight and divide it by g. And that happens to be the same thing that I called m sub s earlier. And that's going to be 509.6 newtons divided by 9.80 meters per second every second. I want to say answer divided by 9.8, and that's going to give me 52.0 kilograms is equal to the mass on the scale. So we can now see that unlike the 65 kilograms she really weighed, this is acting when she's accelerating downward. It's acting as if she only weighs 52 kilograms. Any questions on that? Now that was all part A. For part B, we still have the same thing. We have Fs minus 637.0 newtons is equal to 65.0 kilograms times the acceleration. But in this case, they said the elevator car is moving at a constant 2.0 meters per second. If the velocity is constant, if the velocity is in fact 2.0 meters per second, for instance, and you wait a split second and it's still 2.0 seconds, and you wait another split second and it's still 2.0 seconds, then that's the very definition of the acceleration being zero. Okay? So now you see the right-hand side of the equation is 0, and you find out that the F scale will be 637 newtons, and that also implies that the mass that the scale would read would be 65.0 kilograms. And that's really what they asked for, is what does the scale read when the elevator descends at a constant velocity of 2.0 meters per second. So anybody have any questions on that? All right, so let me show you another type of problem, and this one's going to be example 4.9. So with example 4.9, it's asking us to just calculate the sum of two forces acting on a boat. So I'm going to start off by drawing the boat. So let's say example 4-9. Here's my boat, something like that. And we're going to imagine the keel of the boat is actually parallel to the direction of the x-axis. So I'm going to draw the x-axis this way. and I'm going to draw the y-axis this way, but just like last time where the x-axis didn't matter, on this case, the y-axis is not going to matter. So what we have is two forces acting on the boat. One force is 40.0 newtons, and it acts at an angle of 45.0 degrees. The other force is 37 degrees. And I didn't draw this to very good scale, so I apologize for that. But this angle is going to be 37.0 degrees. And what they want to know is, let's just say, I'm going to do it a little differently. I'm going to call it just plain R. R, which is the general term we use for resultant, is equal to the question mark. Okay? So what this means is we have to actually do an addition of vectors, and we've got to answer what the vector sum of these two vectors are. So to do that, I'm going to use coordinate axes to project these vectors onto the x and y axes so that I can find out their x and y components, because when I have them in component form, all I have to do is add the x components together to get the final x component and add the y components to get the final y component, and then I use Pythagorean theorem to figure out the magnitude of that vector, and I use trig to figure out the direction. So if we try to imagine walking from the tail of the 40 Newton vector to the head by only going in paths parallel to the x-axis and y-axis, I think you'll see that the parallel to the x-axis direction will be in the positive x direction, and the parallel to the y-axis direction will be in the positive y direction. So this is F. I'm going to call this 4 just because it's 40, but your book actually called this FA. Actually, let me just make it an A. I'll just go ahead and say this is FA and this is FB. I did this earlier. I called it F4 and F3, and my students were like, "Ooh, is that the same thing as FA?" So, anyways, this green FA that I have drawn here is FAY, and this green one that I have down here is FAX. So, like I told you guys, when you're first starting off with vectors, it's probably best if you go ahead and decide to write out sine and cosine in each instant, and then use that to figure out which one's the x component, which one's the y component. As time goes on, you can just skip it and just jump right into the component. But what I'm going to do is write the sine of 45.0 degrees is equal to opposite over hypotenuse. The opposite is FAY. The hypotenuse is 40.0 newtons. Notice how I'm not putting any signs in here. When I actually solve for the FAY, that's when I'll put a plus on it to indicate that it's a positive direction, or put a negative on it to indicate it's a negative direction. Now I'm going to write out the cosine of 45.0 degrees. That's adjacent over hypotenuse, and remember, the adjacent side is the side that touches the angle. And if you drew the right angle symbol on the right triangle, the right angle symbol points to the hypotenuse. So in this case, we're going to get FA, oops, there it goes again, changing. We're going to get FA sub x over 40.0 newtons. So now I can say FA sub x is equal to 40.0 newtons times the cosine of 45.0 degrees, which is positive. So I'm going to force the sign right there, and this should be 28.28. So 40 times cosine 45 gives me 28.28. And that's one extra sig fig, so that's nice. FA sub y is going to be positive 40.0 newtons times the sine of 45.0. Of course, sine and cosine are the same for 45 degrees, so this is also going to give me 28.28 newtons. Now I've got to do the same thing for vector B, and vector B has a x component that is positive. You can tell I didn't draw it to scale because in some sense I seem to have made the 30 newtons longer than the 40 newtons. So this vector right here is FB sub x. Now I have to draw the y component, and the y component is in the negative direction, so this is FB sub y. So now I can say that sine of 37.0 degrees is equal to opposite, which would be FBY over 30.0 newtons, and cosine of 37.0 degrees is equal to adjacent, which would be FB sub x divided by 30.0 newtons. And I'm sorry, I know that B turned out ugly. Okay, so now I can go ahead and write out that FB sub x is actually positive, and it's going to be 30.0 newtons times the cosine of 37.0 degrees, and that's going to give me positive 30 times cosine 37. That gives me 23.96 newtons. And similarly, FB sub y, in this case, that's going to be a negative 30.0 newtons times the sine of 37.0 degrees. So 30 times the sine 37 degrees gives me 18.05, negative 18.05 newtons. Now, Rx is just equal to FAX plus FBX, because that's the only two forces we're dealing with. And that means it is 28.28 newtons plus FBX, which is 23.96 newtons. So 28.28 plus 23.96. Did anybody verify that these answers were the same as the ones I got? This is 52.24. You did? Thank you. I appreciate that. So this is 52.24 newtons for that. The y component of the resultant will be FA sub y plus FB sub y. And FA sub y we can see is also 28.28 newtons minus, because the FB sub y is negative, we're still adding, but like I said, it's a negative number, so it's going to be minus 18.05 newtons. So I'll say 28.28 minus 18.05 gives me 10.23 newtons. So now what we have to do is, we were given the vectors more or less in magnitude and direction format, so you should expect to return them in magnitude and direction format. So I draw another coordinate system exactly parallel to the old one because we don't want to change coordinates in the middle. So I'm just going to draw my axes like this. There's my y-axis. Notice it's parallel to the original y. There's my x-axis. Notice it's parallel to the original y. And what I need is an x component that's about 52.4, and it points in the positive direction. So I'm going to say 1, 2, 3, 4, 5. That's roughly 52.24 newtons. And now I'm going to point the 10.23 in roughly this direction, and that's 10.23 newtons. Notice how much smaller that is, because I'm trying to show it somewhat representative. I might be a little too small, I might be a little too big, but it's somewhat representative. Mainly, I want to look at it and say, does this look like it's 45 or bigger than 45 or smaller than 45? In this case, it clearly looks smaller than 45. The resultant vector is this guy right here. And this angle right here is what I'm going to call phi. And the way I work this out is I say r is equal to the square root of 52.24 squared plus 10.23 squared. Now, this is a complicated thing from a significant digit standpoint. So I'm going to show you how I have to do this. Because you're squaring it, that's going to make it, the same number of sig figs, which in this case is 3 for each of those. But when you square it, it could become a really big number. And then when you add it with the other number, that could result in more sig figs or less sig figs. So you got to be careful. So what I'm going to do is take 52.24 and I'm going to square that. And that gives me 2729. And that's Newton squared. But remember, I only had 3 sig figs, so the 9, which is in the ones place, is not significant. So that does mean I still have 3 sig figs. Now I'm going to take the 10.23 and I'm going to square it, and that gives me 104.65 Newton squared. Now that one also had only 3 sig figs, so that means that's good up to the ones place, but the 6 and the 5 are not significant. So when I add these two numbers, I'm only going to have, right there, it looked like I could have possibly forced myself to have 4 sig figs, but it's not going to be the case, because when I add 2729 to 104.6, I get 2,833.7. And we see that the 104 was good to the ones place, but the 2,729 was only good to the tens place. So the ones and the tenths is not acceptable. And that's what we get. Somebody just walked in or came in. Let me do that. So now I'm going to take the square root of that number. And the answer is 53.23 newtons. Oops. And it only has 3 sig figs because that's what the 22,833.7 had. So that's our magnitude. Now our direction is given by the inverse tangent. So phi is equal to the tangent inverse of opposite, which is 10.23, over adjacent, which is 52.24. So when I do inverse tangent, I hit shift tan. 10.23 divided by 52.24 in parentheses. That gives me 11.08 degrees. That's 3 sig figs divided by 3 sig figs, so I should only have 3 sig figs. So my resultant vector R is actually going to be 53.2 newtons at 11.1 degrees. Now remember, this is measured counterclockwise from the positive x-axis, so that's the standard position from mathematics. That's why I can just write it as at. And that's our final answer. Anybody have any questions on that one? All right. Your book asked about a conceptual example. I would like y'all to try to do that, but it isn't one that translates too well to actually doing it online unless I explicitly pull it up, show it to you, and talk to you in real time. So I'm just going to skip that 410, not because you don't need to know it, it's actually quite the opposite. So make sure you study it and ask me questions if you don't understand something about it. But I think that should go. One thing I want to point out to you is friction is often called a force that impedes motion or tries to stop motion. And in some sense, that's right. But if you just think about me trying to walk, let's say to the left, if I want to walk to the left, I sort of lean to the left and push off to the right with my foot. Now, if there's not enough friction on the floor, then my foot would just slip off to the right and nothing would happen. But because there is friction there, when I push to the right in the carpet, Newton's third law demands that the carpet's going to push to the left on me with exactly the same force. So in that way, the friction is actually pushing it to the left, which is the actual direction I'm going. So it's not right to say that friction always impedes motion. In some sense, it can make motion. But if you look at it, the slowest or the smallest level, which is where the two things are in contact with each other, it does impede relative motion there. So if you looked at my shoe was attempting to go to the right, and therefore the friction force was acting to the left, because if my shoe had actually successfully moved, that would have been slipping, but the friction kept it from doing so. So that's in the sense of what we mean by saying the friction impedes motion. It doesn't necessarily impede all motion. It just impedes the motion between the two surfaces that are touching. Any questions on that? At the end of this section, there's a problem solving Newton's law free body diagram discussion. You definitely need to read that. I want you to make sure you do that. I'm going to move on and do example 411, which is called pulling the mystery box. So this is that same box we had earlier. It's 10 kilograms. And this is example 411. So I'm going to draw the diagram real quick and then I'll read the question. So here's our 10.0 kilogram block box. And we have acting on it a force of Fp equals 40.0 newtons at 30.0 degrees. Okay, so that's the actual system, and I'm going to draw a free body diagram in a second, but it says, suppose a friend asked to examine the 10.0 kilogram box you were given in the previous examples, hoping to guess what is inside, and you respond, sure, pull the box over to you. She then pulls the box by the attached cord as shown in figure 421A, which is basically what I just drew, along the smooth surface of the table. Smooth surface means pretend there's no friction. The magnitude of the force exerted by the person is 40.0 newtons and is exerted at 30.0 degree angle as shown. A, calculate the acceleration of the box. And B, the magnitude of the upward force Fn exerted by the table on the box. So B, they want to know the normal force Fn. Okay? So we already showed you how the normal force can be affected. We showed you, for instance, that the normal force when a box is sitting on a table is just vertical. But I mentioned to you, or hopefully I mentioned to you, that if it's on an inclined plane, like you're talking about, a bundle of shingles sitting on a roof or something, in that case, the normal force is perpendicular to the actual roof, and that's not a 90-degree angle, or that's not vertical. So not only that, we saw that when the person pushed down on the box, that made the normal force larger, and when the person picked up on the box, that made the normal force smaller. So here we're going to see another iteration of that. Let me go ahead and draw a coordinate system for our free body diagram. There's my x-axis, positive pointing to the right, my y-axis, positive pointing up. I'm going to say, here's my point particle. Again, until we get to covering torques, we will treat all objects as if they're point particles. Now, the forces acting on this, we got to say what all is touching this box. You don't see it here, but maybe now you do. It's sitting on a smooth surface. So that means there will be a normal force, and the normal force is vertical, and that's the positive y direction. So I'm going to draw the normal force Fn green because that's our positive direction. Now, that's the surface of the table that's touching it. We also have a rope that is touching it, or a string that's touching it. I'm going to draw that vector black because it hasn't been put in terms of components that are parallel to the x or y axes. So I'm going to draw this force like this, and that is Fp is equal to 40.0 newtons, and this angle is 30.0 degrees. And now I've handled everything that's touching it. Again, air is touching it, but we're ignoring air resistance, so I'm not taking into account that. But now we have to talk about the action at a distance forces. In this case, it's gravity. So gravity is actually going to be acting downward. And of course, this is weight, which equals m times g. G is 9.8 and m is 10, so this would be 98.0 newtons. Okay. Now, in order to actually make this free body diagrams useful, I've got to convert that black vector into vectors that are parallel to the x-axis or parallel to the y-axis. And if I tried to walk from the tail of that vector to the head of the vector by only going parallel to the x and y-axes, I'd have to walk to the right along the x-axis and up parallel to the positive y-axis. Both of those directions are positive, so I'm going to use green to indicate this is FP, oops, this is FP sub X, and this is FP sub Y. I'm going to skip the writing of the sine and cosine this time, and I'm going to go ahead and just write out Newton's second law for the X direction is equal to mass times acceleration in the x direction. And in this case, we only have one force acting in the x direction, and that force is 40.0 newtons times the cosine of 30.0 degrees. And that's equal to the mass, which is 10.0 kilograms, times the acceleration in the x direction. But that's the only acceleration we're going to deal with, so I'm just going to call it A. Now, if I take 30 and multiply, or excuse me, that's supposed to be 40. If I take 40 and multiply it by cosine of 30, I get 34.64. So I have 34.64 newtons equals 10.0 kilograms times A. So A is going to be 3.464 meters per second every second, and only that last four is not significant. So there's our actual acceleration in the x direction. The y direction really doesn't mean much here, but once you learn about friction, we'll learn that the friction force is proportional to the normal force. So that's why it's important to be able to do the y direction. So I'm going to go ahead and also do the y direction now. So the summation of the forces in the y direction equals mass times acceleration in the y direction. Now, they said that she would be pulling this block or this box across a tabletop that's smooth. So drawing my coordinate systems the way I have, it seems pretty obvious that the y coordinate of the box is not going to change as she pulls it across. And since the y coordinate is not going to change, that must mean the velocity is zero in the y direction, and it stays zero. And since the velocity stays zero, that means the acceleration must be zero. So we can go ahead and write this as a sub y equals zero. Now I'm going to take my forces and apply them to Newton's second law. So I'm going to say 40.0 newtons times the sine of, someone just came in, let me let them in, times the sine of 30.0 degrees is equal to, or excuse me, that's only the first force. That one's in the positive direction. That's why I just wrote it that way. The other force is in the negative direction. So rather than writing plus a negative number, I'm just going to write minus, and that force is 98.0 newtons, and that's equal to 10.0 kilograms times an acceleration of 0. So, oh, excuse me. I left off something. Hold on a second. I don't have enough room here anyways, so let me just start over with that. So we still have the force Fn. I just left one force off. Whoa, what happened there? Okay. So let me write it a little further down here. I'm going to do it like this.
Um,
Yes.
why was it minus 98 and not divided by 98?
Uh, the left-hand side of Newton's second law is add up all the forces. So you're only adding one force to the next to the next. The next step will require division, so that might be
Oh,
what you're
I
thinking of.
thought we were just stuck to the Y. I only saw the Y one. I didn't realize it was the combined. Never mind.
Oh, okay, no problem. All right, so our force Fn. Oh, let me get it back onto my pen. Okay, my force Fn acting upward. I don't know why I wrote that before, but anyways, the Fn is acting upward, and that's what we don't know, and that's what we want to know for part A. I mean, for part B. Now I'm going to say I'm also adding Fpy. Fpy is going to be 40 newtons times the sine of 30.0 degrees. The sine of 30, of course, is 1/2, so that makes it a little easier. And then we're going to add the weight, but the weight's a negative quantity, so that's the same thing as subtracting the weight, 98.0 newtons. And then the right-hand side is just 0 because you're going to take the 10 kilograms and multiply it by 0. Now that we have this, we can say that the normal force, Fn, plus 20.0 newtons minus 98.0 newtons is equal to 0. That gives us that the normal force is in fact 78.0 newtons. So that's part B, and this is part A. Anybody have any questions on that? All right, so notice how we're doing this. You basically have an equation for the x-axis, you have an equation for the y-axis. In principle, you could have a third equation for the z-axis. You got to break all the vectors up into components parallel to those axes, and you've got to choose their signs, positive or negative. And then from your free body diagram, you can automatically just write down the parts of F equals ma and then solve them accordingly. So hopefully you're learning quite a bit from seeing this, and we now have it done. So I'm going to do a made up example. So this one's going to be made up. Someone else just came in. So made up example. And the only reason why I'm making it up is the one your book does is pretty good, but I like my version a little better. So what I'm going to draw here is a box, and its mass is 10.0 kilograms. And then a little further along is yet another box, and its mass is 20.0 kilograms. And then another box is going to be 15.0 kilograms, like that. And they're all going to be attached to one another by ropes. So here's a rope, and here's a rope. And then there's a force that's perfectly horizontal applied right here. And this is Fp is equal to 100.0 newtons, like that. Now, what we can imagine is the 10 kilogram mass sees a tension T10 pulling it. But once you do that, you got to realize that the 20 kilogram mass is going to think that the rope behind it is slowing it down. So it's going to say T10 points that way, but it's going to think that T20 is pulling it forward. Okay. And then similarly, the 15 kilogram mass is going to think, man, I could really go fast if it wasn't for this stupid T20 behind me. Okay. So what are we trying to solve for here? I want to know the acceleration of the blocks, and I also want to know T10, and I also want to know T20. Okay. Now, these are all sitting on a smooth surface like this. So we'll pretend this is frictionless. And, there's not really frictionless, but you can deal with forces that are so large that the friction doesn't matter. Or you can, for instance, use air hockey tables and that can eliminate it, stuff like that. The main thing is there's a couple ways you could do this problem. You can treat this whole chain of boxes as if it's one object. But when you do that, then you can't determine the internal forces like T10 and T20 because those are internal. Those are forces from one part of the system on another part of the system. But we can use that just to determine the acceleration. And I'm going to do that right now, even though I would normally, when solving this problem, I would do a free body diagram for the 10 kilogram, a free body diagram for the 20 kilogram, a free body diagram for the 15 kilogram, write Newton's second law for each of those, and then solve that system. And that would ultimately allow me to figure out the total acceleration. And I wouldn't even have to draw another one for the whole object. But in this case, I wanted to show you how the whole object could actually be treated, but how limited you are in solving it. So first, let's see the whole system. Whole system. So what we're going to have here is a positive y-axis pointing up and a positive x-axis pointing to the right. And we're going to have just a point object because there's no sense in drawing it out. But basically, the total mass of this is 10 plus 20, that's 30, plus 15, that's 45. So this is going to have a mass of 45.0 kilograms. The things touching it are, of course, the tabletop, and that means there's going to be a normal force Fn acting upward. We also have a force, maybe through a string, maybe by a hand, doesn't really matter too terribly much. We're going to have a force Fp to the right, and that's a positive direction as well. And that is Fp equals 100.0 newtons. Now we've done everything that touched it. Again, we're ignoring air resistance. That's the only other thing that's touching it is air. But now we're talking about action at a distance. And this is weight is equal to, in this case, it's 45 times 9.8, and that gives me 441 newtons. Now, we're not dealing, as I told you, the normal force is, the friction force is proportional to the normal force, and we don't have friction here, so there's really no need to do the y-axis, and I specifically did not ask for any normal forces, so I don't need to draw the normal forces, nor do I need to draw the summation of forces in the y direction. All I care about is the summation of forces in the x direction, so that's what I'm going to solve. So the summation forces in the x direction equals mass times acceleration in the x direction gives me 100.0 newtons. That's the only force acting in the x direction, is equal to 45.0 kilograms times the only acceleration we're really going to have is a, so I don't need to write it a sub x. So a is going to be 100.0 newtons divided by 45.0 kilograms, and that gives me 2.222 meters per second, but we only had 3 sig figs. That was just me showing you an extra digit in case we needed it. Now, I'm not going to take any time to use this acceleration again. I'm going to act like I haven't even done this problem, but I wanted to show you that you can solve this 3 boxes as if it's one big system, and you can only get the acceleration by doing so. Now I'm going to do the free body diagrams for each of them and work a way to solve those. So first off, I'm going to start off with the 10 kilogram mass. I was planning on writing that in black. I don't know how that happened. So the 10 kilogram mass. Our free body diagram here. Again, the y part doesn't matter, so I'm going to ignore it in this case. I'm not even going to draw it. I just want to get the problem solved. So I'm going to say, in this case, the only thing touching the 10 kilogram mass is the T10, and that points in the positive x direction. So I'm going to say T10 is right there, and this has a mass of 10.0 kilograms. And this is the y-axis, and this is the x-axis. And now we're going to say the summation forces in the x direction equals mass times acceleration in the x direction. And notice I'm not examining any kind of problem where the ropes can get slack or where they're going to stretch. So the acceleration of the 10 kilogram box is the same as the acceleration of the 20 kilogram, and that's the same of the 15 kilogram, and that's all the same of the 2.22, but I'm going to pretend like I don't even know that 2.22 and solve it this way. So now in this case, all I have is T10 is equal to 10.0 kilograms times A, and I'm going to call this equation 1. Now I'm going to draw a free body diagram for the 20 kilogram mass. And my free body diagram in this case is X, Y. Again, I'm completely ignoring the Y direction because we don't need any of that information. But in this case, I've got the string on the right that if you ask someone sitting in the box, they'd say, oh, that rope right there in front of me is pulling me. So that force is going to act in the positive direction, and that's T20. But if you ask those same people in the box, they'd say, well, we'd be going even faster if it wasn't for that rope behind us. So in this case, they're picturing the rope going in the negative direction. Notice how we've got T10 in the first diagram pointing to the right, but in the second diagram, it's pointing to the left. This is more or less how it has to be. I'm showing you so you'll know. You've got to repeatedly do this, including for the Atwood machine and all this stuff. Your tensions sort of cancel each other out from one perspective to the other. One way of thinking about it is Newton's third law. Another way of thinking about it is, like I said, imagine you're in the car, and if you're in the 20 kilogram box as if it were a car, you would certainly think the T20 is pulling you forward, and you'd think the T10 is slowing you down. So obviously the T20 is pointing to the right, and the T10 is pointing to the left. Hopefully that will get it for you. Now I can take the summation of forces in the y or in the x direction equals mass times acceleration in the x direction. And when I do that with this case, I'm going to get T20 minus T10 is equal to 20.0 kilograms times A. Again, that A is the same as the other A. I'm going to call this equation 2. Now I need to do a free body diagram for the 15 kilogram mass at the front. So we're going to say 15.0 kilogram. I'm going to draw my free body diagram right here. There's my Y. There's my X. Here's my body. And now the forces acting on it are Fp, which is in the positive direction, and that's 100.0 newtons. And then there's a T20 acting in the backwards direction, like that. So now we can say the summation forces in the x direction equals mass times acceleration in the x direction. In this case, it's going to give us 100.0 newtons minus T20 is equal to 15.0 kilograms times A, and we're going to call this equation 3. So now I'm going to tell you there's a way I can go about solving these three equations to get T10, T20 and A. Notice there's three unknowns, T10, T20, and A, and I have three equations. That's exactly the right number. Notice also how I'm writing what equations I'm using. Doing that helps you realize if you look back later and find out that you skipped one of the equations, then there's no way you got a right answer. But by making a mistake, you could actually accidentally solve it in such a way that it's wrong, but still you'd have a solution. But by writing down exactly what steps you're taking, you'll know exactly which equations you use, and you can tell whether or not you inadvertently solved it before you could. So first off, I'm going to plug 1 into 2. So plug 1 into 2. When I do that, I'm going to say T20 minus 10.0 kilograms times A is equal to 20.0 kilograms times A, and therefore you get that T20 is equal to 30.0 kilograms times A. I'm going to call this equation 4. Okay? So now I've used equation 1 and 2, and now I'm going to take equation 4 and I'm going to plug it into equation 3. So let's say plug.
I'm sorry, really quick. That
Uh-huh.
A, is it not going to be squared? Oh, I'm sorry.
Uh,
No, that's addition. Never mind. Never
yeah,
mind.
yeah, exactly. That's a very normal thing, especially when you're when you're not used to using so much math in a class before. It's often little mistakes like that that happen. So I'm going to plug 4 into equation 3 now. Okay. So I now have 4, which is an expression for T20. So with this in mind, I got 100.0 newtons minus 30.0 kilograms times A is equal to 15.0 kilograms times A. So we can get like terms by adding the 30 kilograms to both sides, and I'll get 100.0 newtons is equal to 45.0 kilograms times A. Now we can see that A is equal to 2.222 meters per second just by dividing 10 by 45. So we got the exact same answer we did for part A, or excuse me, that we did using the system as opposed to using individual boxes. We now have the acceleration, but not only that, we can now go back and plug in the A in equation 1 for finding the acceleration, or excuse me, for finding the tension. So T10 in this case, using equation 1, and the result, T10 is going to be equal to, from equation 1, 10.0 kilograms times 2.222 meters per second, and that gives me T10 is equal to 22.22 newtons, which, by the way, is exactly what Newton's second law suggests. If I wanted to accelerate a 10 kilogram object at 2.22 meters per second, I would obviously need a force of 10 times 2.22, which is exactly what we got. Now I can go ahead and plug A into equation 4. So now I'm going to say equation 4 right here. Oops, lost it again. So equation 4 here is where did 4 go? Oop, there it is. T20 is equal to 30.0 kilograms times 2.222 meters per second, and that gives you 30 times 2.2. Oops. Gives me 66.66. So T20 is equal to 66.66 newtons. So now we've managed to solve all of those problems. Anybody have any questions on that? All right. There's an Atwood machine that's sort of important, and not only that, that's the lab that you're doing. So let me sort of quickly go through that. I wanted to do that, and I wanted to do the ball hanging from the rearview mirror. I might be able to get them both in, but I'm not sure. So we're doing the Atwood machine right now, which is more or less example 413, but I'm just calling it Atwood because I'm doing it with symbols instead of numbers. But this is teaching you a very important technique, one of which is what we just went over, how you break a system up into separate parts. But the other one is how you solve a system of equations. That last example showed you a way of solving a system of equations. This one's going to show you a different way. So what we have here is a pulley that's massless and frictionless. Now we're going to do a butt ton of Atwood machines, and some of them will include friction, some of them include mass, some of them include friction and mass, and all sorts of crazy stuff. Some of them will have inclines, some of them have two inclines, some of them have two inclines of different angles, all sorts of stuff. But what we start off with is a pulley that has no mass and a rope hanging from the pulley, and hanging from that rope is a mass, big M, and I write it as big M to give you the suggestion that that's the heavy one. And then on the other side is a mass that I'm going to call little m, and that's to give you the impression that that one's less massive. The fact that I gave you the m and the m means that you're going to pretend like you know the mass m and the mass big M. Okay, so we're pretending we know those, but what we want to find out is what is the tension in the ropes. It turns out there's only going to be one tension. It's going to be the same in both parts. I'll explain that. And what is the acceleration of the blocks? Again, there's really only going to be one acceleration because if you pull the right mass down 1 inch, assuming the string doesn't get stretched and the string doesn't get slack, then the mass little m is going to move up 1 inch. So when you pull down on the right 1 inch, up on the left 1 inch is going to happen. Similarly, if you pull down on the right of 1 inch in 1 second, then the left is going to go up by 1 inch in 1 second. So that means they're not only are their positions the same, which we'd already figured out, are their motions the same, but now we figured out that their speeds are the same. Again, assuming there's no slack going to happen in the ropes and that the ropes aren't going to stretch, if I pull it 1 inch in the first second and 2 inches in the second, then the left is going to go up 1 inch in the first second and then up another 2 inches in the second. So that shows you that the accelerations for the two blocks are going to be the same. Now that we have that, I'm going to draw a free body diagram for each of them, and I'm going to try to keep my uh, coordinates consistent with that. So I'm doing the left mass right now, and the x-axis really doesn't matter too terribly much, but I'll put it there anyways. Now what we have here is a mass little m. So this is the left diagram. The only thing touching it, excluding air and therefore air resistance, the only thing touching it would be the tension in the rope, and we're going to call that T. I'm not going to label it T left or T right because it turns out that the tension on the left is going to be the same on the right. If you imagine for a second that I was pulling down on the string to the right, then you'd probably think, well, pulling down the string to the right means you've got to rotate that massive pulley, you got to counteract that friction on the pulley, and you got to accelerate the mass on the left upward. But since the pulley is frictionless and massless, then you're just pulling the mass on the left up. That's why the tension on the left is the same as the tension on the right. Now that I have that, I've taken into account the things touching it, but I also have to take into account gravity, the action at a distance. So this is little m g acting downward. I can write Newton's second law as follows. That's going to be T minus mg is equal to ma, and I'm going to call that equation 1. Now, notice when I go up 1 inch for the mass little m, that's going to be the equivalent of going down 1 inch for the mass big M. If I make my y-axis pointing down on the right-hand side, then I don't have to make any new equation that says a on the left is equal to negative a on the right or any of that kind of weird stuff. So it's really smart of me to draw the axis on the right as if the y-axis is pointing down. That way I don't have to write yet another equation. So now I'm going to say I have a mass big M, and according to Big M, it would fall at 9.8 meters per second every second if it wasn't for the tension in that rope. So the rope is actually acting in now the negative direction. Just like we had before, they sort of combat each other. This T seems to be fighting the previous T. But now we have a weight, capital M G, acting in the positive direction. So in this case, we're going to have an equation from Newton's second law of mg minus t is equal to big Ma. So how do we solve such an equation? Well, this is a technique that you would have ran into in Algebra 1 or Algebra 2, but notice the t and the t on the two equations. One has a coefficient of positive 1, the other has a coefficient of negative 1. So the smart thing is go ahead and add them, and that will eliminate one of the unknowns. So I'm going to say t minus mg is equal to ma, and I'm going to say minus t plus big mg is equal to big Ma, and I'm going to add the two equations. You can see immediately that when you add t and negative t, you get 0. But when I add mg and minus negative mg, I can go ahead and factor out the g by calling this m minus m times lowercase g. Similarly, MA plus big MA is going to give me MA plus big MA, but in this case, I'm going to factor out the A, so I'm going to say big M plus little m times A. So now I have the acceleration is M minus M over M plus M, all of that times G. That's a good way of writing it because there's a dimensionless quantity, the M minus M over the M plus M, that's dimensionless. And that's being multiplied by a quantity whose dimensions, whose units we know. So we can tell automatically that A has the right units. It has the units of G, meters per second per second. Now that we have that, we can go ahead and solve for T. And the way I do that is to plug it in equation 1. So plug A in 1 to solve for the tension T. Now that means you're going to have to get a common denominator, so I'm going to go ahead and say T minus mg is equal to m times m minus m over m plus m times g. Now I'm going to say T is equal to m times, I'm getting a common denominator here, so I'm multiplying by m over m plus m over m plus m, like that. Both factors have a g in it, so I'm going to leave that out on the side. Now the other fraction I have is plus little m times big M minus little m over big M plus little m, and then the g is out here. I can distribute this. I'm going to get m big M plus m squared. Notice if this plus right here was minus, I'd have to distribute it there and there, but luckily I don't because this is a positive sign. So in this case, I'm going to get plus m and then minus m squared. You can see that the m squared cancels out with the minus m squared, and the denominator is still m plus m, and the g is still out there. So the way we normally write this is tension is equal to 2m over m plus m times big mg. So that is the tension equation. and that's a Atwood machine. I didn't get a chance to do the ball. You might want to look up the ball. That's another technique for solving systems of equations. I will show you that to you next time, but we have finished chapter 4. You do have a test, an online test, and a practice test that were due Sunday at 11:59 p.m. I've now moved that to Tuesday at 11:59 p.m. So make sure you guys get that done. You're free to go. Thanks for coming. I'll wait for the last person to leave in case anybody has any questions.
Hello, I got a question.
Go for it, David.
When is that in-person test?
Let me check my syllabus real quick. We're still sticking basically to the syllabus, so whatever that says should be correct, and I'm checking it now. I thought it was the 8th, but that could be something else. Am I in the right class? Yes, I am. Here's the syllabus. So face-to-face test 1. Oh, for you guys, the way that works is it has to be done by 10:05. Uh, that would be that's the week after next, right? 10:05, 10:05, 10:05. Oh yeah. So
That is the week after next, but I wouldn't say no to it being moved back to the 8th.
okay. I think that's what I'm going to do. I think I'll go ahead and move that. I'm going to make it come available on October 1st, and I'll make it due October 8th.
If it becomes available, then are we able to set the schedule up before that, or will we only be able to call starting on the
No,
1st?
you can definitely schedule it at whatever time you want. I'm just going to make it available. Actually, yeah, I'll make it available October 1st, so you can take it anytime between October 1st and October 8th. And those dates are included. So it's October 1st through October 8th inclusively.
All right.
Okay. Thanks for pointing that out. I'm glad you did because, yeah, that's a little earlier than I wanted. So I think I will go ahead and allow it to be. You can take it as early as 10:01. That's when it'll pop up. Make sure you let me know if you're planning on taking it at 10:01. But I will send the information on the 30th to the testing centers so they'll know what to do.
Okay.
All right.
All right. Thank you.
No problem. You're welcome. Anybody else have any questions?
I actually had one over the tension.
Mm-hmm.
Not over this one specifically. I was kind of hoping we go over how tension works because I was trying to go over the quiz yesterday, and some of it went over the tension stuff that we hadn't covered yet. I was wondering about like tension at like angles. Is that essentially just like we're just
Yeah, the big
calculating
thing
how
is
deep we
remember
do it?
for tension, it's like a rope. So tension can only act one way. In other words, you can only pull on a rope, you can't push on a rope.
Right.
So that means the force is always parallel to the rope and only acting in such a way that it stretches the rope, not in such a way that it compresses the rope. Does that make sense?
Uh, I guess it was. I forget exactly what it was. I think it was just like trying to get the figure out
Right.
what the tension of the rope was while it was hanging from it. So
Yeah, so if you
because there
if
was
you think
multiple.
about this as a rope attached to say this end down here and some pulling
Uh,
up at this end, the force can only be parallel to that. This doesn't have any ability to pull this way or that way. So you'd have to draw the force as if it's parallel to this, and whatever angle that rope would be, it has to be parallel to that angle. And then it's just a matter of leaving the magnitude as t and then taking and multiplying it by a cosine of some angle to get either the x or y component and then the sine of some angle to get the other component. And then you can just work out, the summation of forces equals mass times acceleration. Or if the object's sitting perfectly still, it'd be the summation of forces equals zero. Or if it's just moving at a constant velocity, it'd also be the summation of forces is equal to zero. Do you have a specific problem you'd like me to give you some specific help on, Colin?
it's from like cheating. So no,
It's okay if you're asking about a homework question. That's not a problem. I don't mind.
no, that's not a homework one. That's one from like the like the practice quiz. At that
Oh,
point, I know it might actually be on the quiz.
oh no,
Therefore, I
I don't
think I
mind
might be
that. No,
choosing
that's
to ask for
exactly.
that.
I mean, if you happen to luck out and have asked me how to solve the particular problem that ends up on your test, that's just you being a good student, solving many homework problems. That's fine. So yeah, if
Mm,
you have one on the practice test that you want me to answer, just go for it. It's no problem at all.
I don't remember exactly how it was. I just remember it was like um, it involved a rope was essentially wrapped around and like there was 100 newtons hanging from beneath it,
Okay,
and
I
the
can find
two
that. Hold on a
angles it
second.
had was 37 degrees.
Gotcha. 37 degrees and 100. You said it was 100 newtons or something?
Newtons. Yeah.
Okay, so what I'm going to do is I'm just going to look in my chapter 4 questions for this class. Uh, and it's not the concepts. This is one where you actually had to answer a numerical answer, not like a yes or no or true or false, right?
Right.
Okay, so I'm pulling up the test bank and looking for tensions and looking for 37 degrees. Looking. Does it have a drawing with it as well?
Yes. There's a
Okay.
drawing.
Okay, so I see one drawing with a 5 Newton and a 6 Newton and a little black ball. Oh, there it is. The two strings with 37 degrees on both sides and a 100 Newton traffic light.
Yes.
Okay. Yeah, that's easy peasy. Let me show you how to do that.
I thought it was going to be easy, but then when I tried to answer, it's like, wait, my
Well,
number's not working. Doing
well, it's
something
not
wrong.
fair to me to say it's easy. Sorry about that, but uh let me see. It's like this, and you basically have a rope this way and a rope this way. Imagine these are straight, by the way. This is 37 degrees, and this is 37 degrees. And they say a traffic light of weight 100 newtons is supported by two ropes as shown in the figure. So what we have here is a traffic light whose weight is equal to 100 newtons. So I'm going to draw a free body diagram. There's my x-axis. There's my y-axis. Here's my object. It has a weight on it. The full pull of gravity, in other words, is 100 newtons. It has a force acting on it that's not parallel to one of the axes. Now, this angle is 37, so this angle is also 37, and that's the way I'm going to use it. Similarly, this is tension, and they both, by symmetry, I think you understand that both of these have to be the same
Right.
magnitude, so I'm just going to call them tension instead of tension left or tension right. But now I got to take the components. So the x component of the one on the right is clearly positive, and the y component is clearly positive. And then the one on the left, the x component is clearly negative, and the one on the left, the y component is clearly positive.
Right.
So what we have here is this guy would be t sine 37, and it would be positive. This one would be negative t cosine 37, and it'd be negative. This one down here would be positive t cosine 37, and this one would be positive t sine 37. So the summation forces in the y direction equals mass times acceleration in the y direction. This traffic light is hanging still, so the acceleration is going to be 0. So what we get in this case is 2t sine 37 degrees minus 100 newtons is equal to 0. And that's actually enough to figure out what the tension is. Now, just for completeness, the summation forces in the x direction equals mass times acceleration in the x direction. It's again hanging still, so the acceleration is zero. But in this case, we get t cosine 37 degrees minus t cosine 37 degrees is equal to zero. So that just tells you t is equal to t. So that's why that part was really not necessary. So now what we can see is T is going to be 100 newtons divided by 2 times the sine of 37 degrees. And so 50 divided by the sine of 37 gives me 83.08 newtons. And the right answer, by the way, just to check it, is 83 newtons.
Okay.
Any questions on that?
No, that one I was just really kind of want to make sure I could
Understood it?
understand how to do that because I was looking at it yesterday and since we hadn't covered tension yet. I was just like really confused.
Yeah. Yeah, that's the big thing is just realize the force can only act parallel to the rope and it can only act
Yeah.
one direction, the direction that stretches the rope, not the direction that compresses the rope from tail to tail. But other than that, it's pretty straightforward to do. But having not seen it, yeah, it's not trivial. So it's kind of cruel for me to say,
Yeah.
"Oh, that's easy peasy." That's me trying to give you a boost of confidence when it actually it's might be smacking you in the head, like acting like you're dumb. But I don't mean it that way at all.
Yeah. I did notice, like, I'm glad you went over the Atwood one because I tried to go over the conceptual yesterday, and the literal second question was the pulley.
Yeah.
It was the tension pulley. Is like, oh,
Well, good deal. I'm glad I got that to you. And was the conceptual due already?
no, that's
Okay.
not due till Sunday.
Okay, I thought I'd push both of them back, but if I hadn't and I hadn't
Yeah,
covered the Atwood in
the
time, I would have pushed it back.
the only thing that was due yesterday was part two of chapter three.
Okay, cool. Good deal.
All right.
Anything else you have there, Colin? Or Melanie, do you have anything?
No, that was it. Thank you.
Okay. Thanks, Colin.
Uh,
Appreciate it.
Bye.
Melanie, you
yeah,
still there?
yeah, yeah,
How
I'm
can I
still
help you?
here. I just had a quick question. Well, actually, Colin answered one of my questions, so that was good. He asked that question.
That's a
But
good thing.
um, when we were going over the tensions on the boxes, when we had to plug in like the equations to one and the other.
hmm
How do you know when to plug in? Like we had to plug in equation four into equation three. How do you know to use equation four versus like the other equations? Because that was messing me up when I was trying to solve
Gotcha.
and I kept putting in the wrong
So
equations.
you like talking about this one right here, or you talk about the Atwood, or is this one a good example for me to help you
Yeah,
with?
that was the example. Yeah, when we were doing four
Okay.
into three.
So what I see is my unknowns are T10, A, T20, and that's it, right?
Hmm.
So what I realize is if I plug T10 in for T20 in equation 2, then I'd only have T20 and A.
Okay.
Uh,
Yeah.
but then if I solved equation 2 for T20 and plug that in equation 3, then I saw that I wouldn't have anything but A. That's what I'm shooting for. I'm trying to one by one eliminate each of the variables that I don't know until I can get it to where only one is left. In this case, because they were so repetitive, one equation had T10, and then the other equation had T10, and then that equation that had T10 had T20, but then the other equation also had T20. That was what made me sort of daisy chain this, where I went from equation one to equation two to equation three, and then once you get to that final part where I was actually able to solve for the acceleration, which you saw where a equals 2.222,
Hmm.
then I was free to plug that in any of those equations. So there wasn't
Okay.
any right or wrong answers to where I plug that A in. It's just any of those equations now can be used with that A to find whatever variables are in that equation. So there's no right or wrong on that. It was just
Okay.
me being able to see the fact that if I plug 10 into 2 and then solve for T20 and then plug T20 into 3, I would only have A, and that's what made me have the idea.
Okay. Okay, that makes more sense. Okay, so it looks like I was messing up on doing the first plug one into two, and then I got a completely different answer, and that's why I was confused. Okay, that makes perfect sense now.
Gotcha. Yeah, and sometimes, I mean, there's other ways. There's no quote unquote single right way. So any of the
Mm-hmm.
techniques you learned in college algebra, like the Gauss-Jordan method with
Oh,
matrices, all
forgot
those
about
things are completely fair game when you have systems of equations, long as they're linear. That's the only
that.
thing that bums you out. But to be honest with you, I've never had to use it in a nonlinear form. So all of those techniques are fair game. You can multiply one equation by a constant and then multiply another equation by a constant. That could make maybe one of the coefficients of one of the variables have equal but opposite coefficients, and then you could add them, and that gets rid of one of your variables. That's sort of like what I did with the Atwood machine, except the Atwood machine
Mm-hmm.
was already primed with exactly +1 and -1 coefficients.
Okay. Okay, got it.
And that's sort of
Thank
what we're
you.
doing here is I'm trying to show you examples so you'll see exactly what techniques we can use.
Okay. Yeah, okay, I get it now. Thank you for that.
You're welcome. Anything else, Melanie?
No, that was all.
All
Thank you
right.
so much.
Good deal. Don't forget to get ready for your test, and the practice test is going to give you a great deal of confidence. When you start doing that, you'll feel you should either do so well that you get a good deal of confidence that you know what you're doing, or you can
Mm-hmm.
say, "Oh, well, this is my weak spot. Let me go to the
Mm-hmm.
chapter quizzes and work on that chapter 3 material or
Oh
whatever."
yeah, the because I had tr done this class a previous semester and
Hmm.
I'm redoing it for that. This was my weak spot, so now I'm hitting it again. I'm like, oh, I'm seeing it again. Let me try and get it the first time again.
Sometimes the
Uh,
second time is all you need. It's not necessarily that, I'm doing a great job and somebody else did a bad job. It's just sometimes you just
mm,
need a second look at it.
yeah, that I think that was my problem. I didn't have like enough time to practice and then get better
Yeah,
at it. So
physics really takes a lot of time unless it's just something that you've been doing from a young age, which most people haven't. But occasionally you'll
yeah,
find somebody that's been doing it since they were in third grade or something.
I can't imagine.
Yeah, for real,
Okay.
right?
Yeah, thank you so much.
You're
Have a
welcome.
good weekend.
You too. Take care.
You too.
Bye bye. All right, I'm gonna go ahead and stop sharing, and we're gonna call it a day. I was gonna solve the hanging or the fuzzy dice problem, as I call it, hanging from the rearview mirror, but I decided not to. I'm tired. Have a good day, folks. Bye bye.